Hello. It is Wednesday, my dudes. So, welcome back to Networks and Cybersecurity. I had to double check. Is it really Wednesday already? Luckily, I can see my calendar on another screen, so it's less embarrassing. So, hope everybody is doing well today. I just finished grading those previous homeworks. You got your next one due at some point. I think you still have a while for that one. Was it Friday, Monday, something like that? And that homework is primarily a TCP homework, so I thought, well, let's do a little bit more on TCP before we go into the lab on it. So we'll probably do the lab on Friday, and we'll do a little bit more on it here today. And then we'll also probably have our first red versus blue team challenge shortly at some point. And hopefully everybody is familiar with the VM by now, because we'll almost certainly be using the VM for that. So to start off today, I'm going to go over some news in the tech sector before we get into the transport layer. So let's see what's happening today. Normally I don't bother too much with current events, but it's just such an interesting time in cybersecurity in particular right now. First, I believe tomorrow the Supreme Court hears Oracle versus Google, which is going to be a truly landmark case for the United States. It's going to tell us if an API, so something like Java's API, like system.out and math.random, if that kind of thing can be copyrighted. And if it can, then a lot of people are about to get sued, and it's going to be very hard to make software. It's going to become a very miserable profession if Oracle wins. On the other hand, if Google wins, Go will continue to be a blatant but inferior ripoff of Java in many ways, and various other implications there. So the equivalent argument here, right, is whether or not you can copyright, let's say, the way in which the buttons on your microwave are used. You can copyright, let's say, the exact design of the microwave. Can you copyright the way in which buttons are used? Can you copyright the quick 30 button? Can you copyright start, stop, add time, defrost popcorn? Who knows? Currently, the answer is usually no, but no one's really ever thought about it too hard because the law is pretty tech illiterate. So we'll see how that goes. John McAfee, a very famous hacker, the founder of McAfee Antivirus before he left it many years ago, has been indicted for tax evasion. I believe he resides in Spain right now. I just want to point that out as a demonstration that there is no escape from United States law enforcement. Even if you live in a foreign country, you have to go really to the ends of the earth to get away from the Internal Revenue Service. And a friendly reminder that if you are born a U.S. citizen, someone said McAfee antivirus is still terrible. He admits that it's terrible and basically says that on any occasion that he's asked. He says, it's absolutely horrible. I'm ashamed that my name is on it, and I hope that they die in a fire, basically. And this is a guy who is a self-confessed drug smuggler, among other wonderful things. So the fact that he's ashamed to have his name on it is truly a testament to how bad McAfee is. But what I was saying, if you were born a U.S. citizen, then you must pay your U.S. income taxes no matter where you reside in the world. So if you move to a foreign country like Spain and make a ton of money, you still have to pay your U.S. income taxes, unless you renounce your citizenship, which costs money. And if you don't, then they will indict you in the foreign country where you live and extradite you to the U.S. to serve in prison. So truly a hilarious paradox indeed, because there is no way out without paying, and it is not cheap to renounce your U.S. citizenship. But hilarious for McAfee, or hilarious for us to look at McAfee's plight. He's truly a funny guy. The Earn IT Act moved into the U.S. House again. This follows what I will discuss probably on a later optional presentation. But let me ask you guys a simple question. If you want to pass a bill to restrict the privacy rights of Americans on the internet or to have more control over the internet, what do you say you're doing? This is true of pretty much every single bill that restricts the internet or restricts privacy. What do you say you're doing when you want to pass that kind of bill? You want to pass a bill that reduces the amount of allowable encryption, reduces the different kinds of tech that's available to communicate, increases the liability of a web provider. Somebody commented it's for safety. You're on the right track. Someone said stopping the Chinese. No, that doesn't work. Only a certain percent of the population cares about that. Everyone cares about safety. It's more specific, though. It's not just safety. It's a certain kind of safety that you've got to talk about when you're trying to pass a real draconian cybersecurity bill like EarnIT. EarnIT will essentially outlaw the encrypting of your communication information. It will make it so that any entity that transmits your communications, so be it like WhatsApp, Signal, standard text messaging, Skype, whatever service you can use to communicate, must, if law enforcement requests, be able to and actually give out the information as to what you sent over your system. So it'll basically make private end-to-end encrypted conversations illegal. And they're doing this, of course, to stop child porn, right? To stop pedophiles. That's what it always is. It's pedophiles every time. So just a lesson to be learned about the internet, that pretty much all internet litigation, anything that the government looks at in terms of the internet, whenever they're trying to crack down on something on the internet, the excuse is always to stop pedophiles. And something to consider, we made a arbitrary service for our homework, a simple UDP client and server to send arbitrary strings, right? If you make any kind of service on the internet that allows other people to send arbitrary data to you, so any kind of hosting, any kind of display service that allows you to send arbitrary data, somebody will use it for child pornography. That is a guarantee. So get ready to, deal with that, right? This is true of pretty much every platform, and most developers learn this the hard way. If you make some kind of web forum, anything, no matter how innocent, jerks will come along and mess with it, because that's just what they do, right? And the last piece of news is that AT&T has effectively ended DSL in America. It will no longer be selling DSL to residential customers. You can now only buy DSL if you were grandfathered in, so you already had it, or you are a business customer. They're still leaving it available for business customers for some time. So their plan is to deploy fiber to the home to the rest of their customer base eventually. In the meantime, if you live in a DSL-only area, you are in pretty bad luck right now, especially if you try to sell your house, because nobody's going to want to live in your house when it has no internet access, and it won't, because they won't be able to buy the DSL that you already have. This comes as AT&T finally fulfills its legal obligations to roll out fiber to the home to some millions of Americans after their merger was approved almost a decade ago now. So no more DSL pretty much in the United States, which is good, because DSL is terrible and there's really no reason that you should have it today, aside from that we have not upgraded our grid in many decades. So hopefully this sparks some innovation. Someone asked if I saw that the House wants to break up big tech. Well, that's kind of an ongoing thing that's been going for so long, so who knows if they'll ever actually succeed. The EarnIT Act has a fairly good chance of passing, like all of its predecessors that essentially wanted to do the same thing. This one has quite a bit of interest behind it, so we'll see how that goes. So now let's get into more about TCP. So we learned about the three-way handshake at the beginning. I also want to point out that there is a handshake to end the session. So the handshake at the beginning we learned was you send a SYN, you get a SYN ACK from the server, and then you send back an ACK, and that can contain your first payload, and then the conversation begins. So then you'll have the back and forth of data with acknowledgments for each data that was received. Now when you're ready to finish the connection, so this is whenever the client closes the socket, the proper way for that to happen, and I believe Java will do this for you automatically, you'll see in the lab, is the client sends a fin, and then the server responds with an ACK and a fin of their own. It's at this point that the client can actually shut down, because the client needs to send one more thing at that point. It needs to send out the final ACK to the server's fin. So when the client sends out that fin message, it actually waits for the fin from the server before it fully shuts down. That means that if a client is behaving correctly, they stay open for a few moments after they send their fin. That means if your application goes unresponsive and you have to kill it, this doesn't happen. And so the application might not, the session might not realize that it's closed for some time. So sessions need to have some sort of timeout if there's no communication on them. It also means that if your application is just badly configured and it just sends that fin when you mash the X, then technically you haven't completed the closing handshake, the termination of the session. Once a session is terminated, you have to start all over with the SYN-ACK handshake in order to get it started again. So, any questions on the opening handshake or the closing handshake, the SYN handshake or the fin handshake? We will look at these both in the lab, and you definitely don't have to do either of these when you implement TCP. This all happens under the hood, invisible to you. We'll go over how that looks in Java. Well, actually, we've already gone over it. When you open a server socket and do server socket.accept, what happens at that point is that the handshake occurs, and then at that point the session is established, and the session is basically the socket at that point. The socket writes into that session at that point. All right, so when do you use TCP? When do you use UDP? In case it isn't immediately obvious, so TCP goes when you need all the data. So when the data has to arrive reliably, you would always defer to TCP. So file transfers are always TCP. That's a given, because if you lose a segment, if you lose a packet of the file, of course, you can't piece the file together properly without it. So file transfers, TCP. Most web applications are TCP because most web applications are just file transfers, basically. So when you visit a website, it sends you a bunch of files. When you visit their front page, it sends you index.html, it sends you all the embedded images, whatever, and then your browser just reads them in the order that it's presented based on whatever markup language they use to tell you how to read it. So since web is mostly just the transmission of files, generally it goes over TCP. So that means pretty much all HTTP traffic runs over TCP. Email should be TCP. You want to get the whole message. Most encrypted data transmissions also TCP, because you need the session. So generally anything that's encrypted is built on top of TCP. Not everything, but most. So whenever reliability is a high concern, or getting all of the data is a high concern, or getting all of the data in order is a high concern, then you would switch to TCP. So I would say that TCP should probably be your default choice, and then if you have a particular reason that you want to use UDP, you would switch to it. But let's go with why should you use UDP specifically. So when low latency is the priority. Now why then do I say that TCP should be your default? Well, because this is an example of premature optimization. If latency is a problem, and you definitely know for sure it's going to be a problem, then you can start with UDP. So that includes things like video games and voice over IP. DNS, which we haven't covered yet, needs to respond very quickly to requests. Video streaming needs to happen sometimes very quickly, especially like live video like Skype or something. So in these situations, you know you have a high requirement for latency. You can start with UDP. But in most situations, you're not sure if the latency of TCP will be good enough. And it probably will be. So I would say start with TCP. And unless you have latency problems that can't be solved, then you probably should stick with TCP. But if you're transmitting data where the individual packet is not very important, you can also use UDP. I would say at this point, unless, again, you have a particular reason why you think latency is going to be a big concern, you can still use TCP just because even if it's not that important, it's probably better that it arrives than that it doesn't. TCP, for kind of the reasons I've described and sort of that default to TCP sort of ethos that I'm trying to espouse here, has basically eroded away UDP slowly and steadily. So most internet applications have shifted away from UDP. At one point, it was probably like, I don't know, 70-30, 60-40. It's a total spitball. I really have no idea. But at one point, UDP was a fairly large chunk, and now TCP is probably like 90% of web traffic. Because TCP has web and most other like high reliability platforms, that already gives it the bulk of traffic. In terms of data, at least, for sure. UDP, when it's used, is typically used for small pieces of data. So like UDP was pretty much universally used for voice over IP because of latency issues, but it's also started to go over to TCP. So maybe when we're in the lab, you can look at Discord, for example, and see what Discord uses today. And why, again, have some applications shifted away from UDP since the early 2000s or so? Well, because latency has globally gone significantly down. Internet speeds have gone up and up and up. More people have access to fiber, 4G, soon to be 5G. As latency becomes slower and lower, so as your packets arrive where they're trying to go quicker, the overhead of TCP, which is that everything has to be acknowledged so that you have to go two ways for everything to actually be confirmed, that overhead becomes smaller and smaller. So when the one-way trip was 200 milliseconds, UDP had a lot of advantages because sending a packet was 200 milliseconds quicker than having to send one and then get a response back before you can continue, which is not how TCP works necessarily. We'll go into that in a bit. But as internet speeds have gone up, so let's say that the average ping is now more like 40. Well, 80 is not that much worse than 40. Both are imperceptible to humans in most situations, so why not just switch to TCP? The other hand, packet loss has also improved over the years. So as connections have become more reliable, packet loss is less of an issue. And that means that the reliability guarantees that TCP gives you have become less and less important. So it's actually in UDP's favor a little bit there, that the reliability concerns are less important. But no matter how reliable your connection is, it will eventually drop at least one packet, right? So if the reliability concern is there, you still have to address it somehow, even if the reliability itself has gone up significantly. Let's talk about some more advantages of UDP then, since I'm sort of leaning in TCP's favor here. First of all, congestion control is sometimes a disbenefit. So TCP automatically slows down when its window shrinks and it delays sending packets. So if TCP senses that there is congestion somewhere in the network, it slows down sending packets. But in some applications, if a segment isn't sent right away, so this again, voice over IP or gaming, in these situations, if the traffic isn't sent immediately, as soon as you click the mouse, as soon as you say the word, there's really no point in sending it at all, because if it doesn't arrive with a very, very meaningful delay, so in a very short time window, then it's already expired, basically. You wouldn't want to have a VoIP call where if somebody drops a couple packets or there's some congestion, it just cuts them off completely and then their whole voice arrives in like 3 to 5 seconds. That'd be very jarring. And online games, for example, well, they send data as fast as possible, and it doesn't matter if all of it makes it. So they basically update you on the state of the game frequently. So if you complete the bonus for this homework, which is a TCP homework, then you have to update the clients on the state of the little drawing application, drawing game, whatever you want to call it. So when you update the clients on the state of the drawing game, if they miss one of those updates, it's not a problem. They'll just sync to the next one. And this is true of most games, that if you miss an update, it's fine. You'll just sync up to the next one. But there's nothing preventing you from building your own segments. So you can take UDP, which is the bare minimum on this layer, and you can add the functionality that you want to it from TCP a la carte. So you can always add TCP-like functionality to UDP. It's tough, but there are many examples of applications out there where programmers didn't need everything from TCP and they didn't want the overhead imposed by the other stuff, so they just built upon UDP by adding their own headers. Remember, headers are abstractions, they're imaginary. It's just the first so many bytes of the packet. There's nothing stopping you from having more bytes at the beginning of your packet that you also treat as headers and you decode on your receiving end and handle accordingly. So let's say the first 4 bytes of your custom UDP payload are actually the sequence number header or something like that. There's nothing stopping you from doing that. So it's common to add acknowledgements and sequence numbers. Those are the 2 main things that people add to UDP, I would say, and then you can get other things like congestion windows or other features that maybe even TCP doesn't offer. So you can always build in your own functionality. But technically, you're now at the next layer up, right? Because you're dealing with the payload of the UDP segment. So now you're actually talking about the application layer because you're messing with the payload of the UDP segment. So another advantage that UDP can have is in one and done exchanges. Some exchanges on the internet and in real life are just really short, send it and then be done with it kind of communications. These don't merit the overhead of establishing that TCP session. So you have to do that initial handshake, and then you have to do the the closing handshake, the fin. So you have to do the SYNAC handshake and then the FINAC handshake at the end. That's a lot of effort. So when you're walking by somebody in real life, you say, "What's up?" They say, "Not much." You say, "Not much," and then you keep walking. You don't shake hands, greet one another, then exchange those pleasantries, and then say, "All right, farewell." And they say, "Yes, farewell." And then you walk away from one another. That would be the functional equivalent there. So if you wouldn't do that in real life, it doesn't make sense to do it for quick communications on the internet either. So the handshaking itself adds a pretty significant delay, right? 2 round trip time delay. Why is it 2 round trip time? By the way, why does handshaking add a delay of 2 RTT before the conversation can start? So there's 1 trip there for the SYN, and then I SYN ACK back. That's 1 round trip. So SYN there, SYN ACK back. That's 1 round trip. Then the ACK, right? That's half a round trip. So why do we call it a delay of 2 round trip time before the conversation actually starts? I guess I'll ask this in the lab if I remember. If not, ask me later. I will answer, but I prefer to leave it to the lab, but hopefully I remember to put it on there. Okay, so unless someone answers in chat, by the way, then I'll just leave it off. So thread and socket limits. As you've seen, if you've started your homework or if you've just seen the example, so TCP will typically dedicate a thread for every client, and it always dedicates a socket per client. And a socket is a non-zero amount of system resources. So if there's 1,000,000 clients, that's a lot of sockets, and that's a lot of resources being used to open up those sockets in terms of just memory, and threading is also pretty expensive in terms of overhead. That's less true today than it was in the past, but threading is still relatively expensive, even as there are massive multi-core server processors that really can handle billions of threads. It's a little expensive. So if many of those users aren't talking, and that's going to be true of most applications, most of your clients at any given point probably won't be transmitting anything. So you're wasting quite a bit of resources when you use TCP in that way. UDP can handle clients in the same thread in the same socket. So remember, UDP just opens up one receiving socket and it just listens on the the same one for everybody. The downside is that everybody goes to the same buffer and that there's no congestion control. So then if all of those million people start talking at once, there's no way UDP will have the resources to process all of their requests. But as you saw in the exam, at some point, many of you were talking to the server at the same time, and some of you were trying to connect to it repeatedly in order to get it to transmit the secret. And so there were a few people basically DDoSing it, so spamming it with messages at the same time, and it was still able to respond to your requests, generally speaking. So even a very weak server like the VM could handle a pretty large number of clients on one UDP socket before it tries to break down, as long as the information being sent is fairly small. So if you're building an application that only has a few users, you might still use UDP because you don't need a separate socket for every individual. All right, more on TCP then, more on the TCP implementation and such. So we've said that when a packet is dropped or a packet is lost, TCP guarantees that it will be received eventually. So what happens actually when a packet gets dropped? So it's something happens to it over the wire, and the receiver just never gets it, which means that the receiver never sends the acknowledgement that they got it, because they didn't, right? So what happens then? How does TCP ensure that you still get your information? So the packet's lost, the acknowledgement's never been sent, now what? So the receiver doesn't get it, they don't send the acknowledgement. That means that the sender has to figure out that they need to retransmit it. So how does the sender figure out that they need to retransmit it? Well, whenever the sender sends a packet, they have some sort of timeout, and if they don't get an acknowledgement within that timeout, so just a timer that they set, if they don't get an acknowledgement within that time, then they will retransmit the segment to the receiver. The receiver can't know that it didn't get something unless it got stuff beyond it and then stuff arrived out of order. That's another story. But generally, the receiver doesn't know that it didn't get something. So it's the sender's responsibility to retransmit, actually. So the sender waits a particular time, and then it retransmits the segment, and it repeats that until the segment is acknowledged, or it's reached the maximum number of retransmissions. So TCP has a max. It depends on the implementation, but you'll have a max number of times you attempt to retransmit before you give up on the connection and basically assume the session's been abandoned and close that socket. So if you receive on the receiving end a retransmission, if you've already acknowledged it, you just discard it. So that can happen, right? The sender's timeout is reached because the receiver just doesn't acknowledge in a timely fashion. When that happens, the sender retransmits, but then it probably gets the acknowledgement later. So after it's retransmitted already, then the receiver's acknowledgement finally shows up. In that case, the sender knows that it's been acknowledged. It doesn't care if it's an acknowledgement of the retransmission or of the original. It still knows that it's been acknowledged. But on the receiving end, you don't have to do anything with that retransmission. You can throw it away. So on the receiving end, you always check the sequence number and see if you've already acknowledged it. And again, you only retransmit a certain number of times before you abandon the session. But it should be pretty obvious that sending a packet and then waiting for the acknowledgement are very inefficient. So you don't want to send a piece of data, wait for it to be acknowledged, send a piece of data, wait for it to be acknowledged, send a piece of data, wait for it to be acknowledged. That'd be very inefficient. You would have to wait that whole round trip time for every piece of data. So instead we have something called pipelining with TCP. And a pipeline is basically a stream of your sent but not yet acknowledged packets. And then also the potential to send more. That whole process we'll see is called a window. So the pipeline is just the sent but not yet acknowledged packets. So if we say that we can pipeline 10 packets in our TCP connection, that means that at any given point there can be 10 packets. Usually this is measured in bytes, by the way, instead of packets. We can say that there's 10 packets in our pipeline. So that if you can send 10 at any given time without an acknowledgement, then we say we have a 10 packet pipeline. So again, normally in bytes, we would say we have like a 1,000 byte pipeline. In order for this to be possible, the sender and the receiver must both have some sort of buffer. And sequence numbers must be unique to packets, and they must increment in sequence and sequentially, right? So the first packet might be sequence 500, the next one might be sequence 1000. They have to go up in a consistent way. So TCP fits the bill, remember, by using the byte as its sequence value. So how many bytes have been sent. TCP fulfills both of those requirements. So both ends have a buffer typically, and then the sequence numbers go up in proportion to how many bytes you've sent. How does UDP handle a pipeline now? Well, it can't. So UDP can't handle a pipeline because it doesn't care about acknowledgments. UDP is fire and forget. So UDP doesn't have any kind of pipelining. But how would you build pipelining into UDP if you wanted to? So something to think about as we go through a couple of these implementations that TCP might use. One of the easiest retransmission implementations is go back N. So this is what the pipeline looks like from the sender's perspective. The entire window, this N, includes the cyan bytes, which are sent but not yet acknowledged, and then also these gray segments here, which are more bytes that we could send. So if this is a pipeline of 10, then we have this many used up, and the rest of the pipeline is still available. So the grays are, we have not yet transmitted those segments. So we still have some room in the pipeline to transmit some more. Once the window, we call this the window, is full, we can't transmit anything else until we start getting some acknowledgments here. All right, so blue have already been acknowledged. The cyan are sent but not yet acknowledged, and gray is we can still send these, but we haven't yet. And white is not usable because it's outside of our window. So in this case, our pipeline is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of whatever arbitrary unit this is. So it might be packets, might be bytes, might be some multiple of bytes, whatever. And the next sequence number that we are going to send is the first gray packet, obviously. So we've gone up to the last cyan one in sequence numbers. The next sequence number will be the first gray packet. So typically, again, we achieve this in bytes because sequence numbers are directly tied to bytes. It uses a window between n and n plus size. So if the window is n big, you've got n and then n plus the size of the window. A little bit confusing with that picture because it's called window size n, but anyway. Where n is the first not yet acknowledged sequence number. So the first not yet acknowledged sequence number, that is the sequence number of the first cyan unit, that is the start of the window, and then the end of the window is n plus size, so the size of the window being uppercase n in this case example. So n is the first not yet acknowledged sequence number, size is the size of the pipeline, in this case in bytes. And because of how we visualize this when we draw it, so like this picture for example, it's called a sliding window. And it's called a sliding window because as these cyans turn blue, as they become acknowledged, the window will just slide over. It always starts at the first cyan square. So it always starts at the first cyan square. So as these squares go blue, it will slide over to the right, and that's why they call it a sliding window. Okay. So either the application layer is blocked or packets are buffered when the window is full. So if the window doesn't have any room, then the application can no longer send traffic until the window has some room in it, or the application continues to send traffic to the operating system, and the operating system stores that traffic in some kind of buffer. So you have some kind of memory for where your packets sit. They get queued up until they are ready to enter the window. So in this situation, let's say that the entire window was full, the whole window was cyan. Well, actually, the white area would represent the queue where the window will go later, right? So this is basically the next to be in the window, but currently outside of its scope area. An acknowledgement in go back n is cumulative. That means that if you acknowledge, let's say in this example, the very last cyan square, you've actually acknowledged all of the squares before it. So if you acknowledge any square in the window, you acknowledge all of the squares before it. That means that in the event of a timeout, the sender has to retransmit everything that has not yet been acknowledged. So if there's a timeout, the sender just retransmits the entire window, all of the cyan, all of the not yet acknowledged packets inside of the window. Since the acknowledgement is cumulative, some implementations of go back in will just discard traffic that they get that's out of order. So if you get a, I'm going to keep calling them packets, even though technically I mean bytes. So if you get a packet, and let's say you get packet 4, you were expecting packet 3 next. So now you get to decide what to do. So you can either keep 4 until you get 3. That means that you have to buffer it, and you also have to, in your implementation, somehow reconstruct them. So after you get 3, your machine has to somehow put them back into the proper order. That's not hard, but it's also not nothing. So it requires you to have a little bit of effort in your implementation, and it requires resources to store it somewhere, put it back in order. That takes system resources. So, and obviously buffer space to hold on to 4 while you're still waiting for 3. So if buffering isn't an option, or the overhead imposed by having to put things back together again is too much for that particular system, if you get 4 but you haven't gotten 3 yet, you'll just throw 4 away. And that means that 4 will obviously have to be retransmitted because you've thrown it away. It means you haven't acknowledged it. If you sent an acknowledgement and then 3 didn't show up, then you would be out of luck because the window would have already moved on. The other problem with go back in is that retransmitting the entire buffer is relatively costly. So go back in is actually pretty bad for lossy connections that have a lot of lost packets, because you have to retransmit the entire window anytime there's a timeout, which is pretty substantial. So it depends on the implementation whether you want to handle out of order traffic, but you always have to retransmit the whole window if there's a timeout. The advantage is that we only need to maintain one timer at a time. So the oldest sent but not yet acknowledged message is the only one we need to have a timer for. So the very first cyan block is the only one we have a timer for. And then we reset the timer whenever we get a new acknowledgement. So whenever any kind of acknowledgement shows up. So whether it's just for the very first unacknowledged one or it's a cumulative one, we reset the timer and we scoot the window up and then we wait. Right? So we only have to maintain one timer at a time. That's a pretty nice advantage in terms of resources on the receiver's side and on the sender side. Another approach is selective repeat. So SR, selective repeat, is a little bit closer to what TCP actually does. So it's similar to go back in, but more similar to what TCP actually does, which we'll look at the end. So like go back in, selective repeat also has a window, and the window still starts at the first sent but not acknowledged byte. So it actually looks the same. But selective repeat buffers out of order packets. In order to buffer out of order packets, what extra things does selective repeat have to do compared to go back in? So let's assume that it's similar to go back in, except that you can get out of order packets. What else does that mean that selective repeat has to do on top of go back in? Any ideas on what selective repeat might have to do on top of go back in order to be able to receive and acknowledge packets out of order? What else might selective repeat have to do in order to receive and acknowledge packets out of order? Someone said the sender would have to keep a separate timer for each sent but not acked packet. That's true. You have to keep a separate timer for all of them. It also means you have to send a separate acknowledgement for all of them, right? So let's look at the picture first. So how does selective repeat work? So the window is the same in terms of how it's pictured, but now you see that in addition to the cyan squares, there are also some blue ones that are interspersed. So although the window still starts at the first cyan square, so the first sent but not acknowledged packet, we have now the ability to acknowledge some out of order and then put them back together again into order. So we're acknowledging all of our packets individually, but otherwise the window is still a sliding window. It still works the same way. We still scoot the window over whenever we acknowledge the packet at the left, or the oldest packet in the window. So what extra things do you have to do? You have to have a timer for every packet. Go back and just had one timer for the whole window. Now you have to have a timer for each one you send. So every time you send a packet, you start a timer for it. If the timer expires, you retransmit that packet individually. That's a lot of extra resources on the sender's end in terms of timers, but it avoids having to retransmit the whole window at once, which is a pretty big perk. Now the receiver must individually acknowledge each packet, so that's a lot of overhead on the receiver's side, but now you can assemble traffic out of order, and again, you don't have to receive the whole window again if it expires at any point. And the receiver must now be configured to also acknowledge packets that are below the current window's starting point. So why is this true of selective repeat but not go back in? So the receiver has to be configured to also acknowledge packets that are below the window here. Why does that have to be the case? So go back in, you could just ignore packets below the window there. Why is it the case that selective repeat has to acknowledge these? Any ideas? Why does selective repeat have to acknowledge packets that are below the current window's starting point? These blue guys here, why does it have to acknowledge these? Possibly a mystery to leave for the lab, but if I can't phrase it as a question, or if I put it on one of these slides here, I might have accidentally put it here. Did I? No, I don't think I did. Okay, so hopefully we'll leave it. Someone asked, so it can reorder. Why does it need to be able to do that in order to reorder? Would the window ever move if the packet below the start was acknowledged? So the window only moves when the packet at the start is acknowledged. So it only moves when the leftmost packet gets acknowledged. So why would you ever need to acknowledge something that's below that leftmost level? Think about a situation where the rest of the window has been acknowledged, but you're waiting on one to be acknowledged, the very leftmost one, but the entire rest of the pipeline has been acknowledged. All right. So what TCP actually uses is a cumulative acknowledgement system. So this kind of moot the whole selective repeat thing, but this part it actually inherits from the go back in protocol. Someone said the sender would have to keep a separate timer for each thing, and then in case the sender retransmitted it. So if the sender retransmits the packet to the receiver, then the receiver should re-acknowledge it, right? Why? So let's say, back to that situation, only the leftmost one is unacknowledged, right? Here's the problem. Acknowledgements can get lost too, right? If an acknowledgement gets lost and the whole pipeline is full, except for the one message on the very left, so the very first one. And actually, it was supposed to get acknowledged, but that acknowledgement got lost. And so what the sender does is it just retransmits it, thinking that, okay, the receiver didn't get it. If the receiver is not configured to acknowledge those unreceived messages, it'll just not. It'll discard it like go back in does. And in that case, the sender is trapped forever because the sender's window can never advance, right? At that point, because the receiver will never acknowledge that packet because it's below its window. And so basically this is required in order to deal with the fact that acknowledgements sometimes get lost too. So the sender's window cannot advance until it gets an acknowledgement, whereas the receiver's window can advance immediately as soon as it acknowledges something. So as soon as the receiver gets, let's say these two, it'll advance its window right away. Okay, but the sender is still here because it hasn't gotten the acknowledgement for these two yet. If one of the acknowledgements for these two don't show up, then the sender is stuck forever unless the receiver will acknowledge it on a retransmit. So that's why the receiver needs to be able to acknowledge things below the current window start in selective repeat. Fun, right? Okay, so TCP actually uses a cumulative acknowledgement similar to go backends. It sends only the first missing or expected byte as acknowledgement. So we went into this briefly when we looked at the header. The acknowledgement is always the next expected byte, right? So whatever the next expected or the next missing byte is, that's the acknowledgement that we send. So in practice, we try to acknowledge every message. So it's usually similar to how selective repeat works anyway, just because we're sending an ACK for every message. But if we missed a few and then picked it up again, we would just send the acknowledgement of the next byte that we are expecting, so the next missing byte. So basically the first gray square in the window, that's the next byte that we're expecting. If that window is made up of bytes, that's what we send when we send our acknowledgement. What to do with out-of-order traffic is actually up to the operating system. And the interesting thing is that two systems that are configured differently in terms of what they do with out-of-order traffic can still talk. So I want you to think about this and rationalize it because it's a little bit counterintuitive. You would assume they'd have to cooperate, but they don't actually. Some can keep and buffer their out-of-order traffic, and some can discard their out-of-order traffic and wait for a retransmit, and both of those implementations can talk to each other perfectly fine. So in any combination of sender and receiver, right? So just think about it a little, and you'll see that there's actually no situation in which that's a problem. It obviously creates an inefficiency when one side is doing it and one side isn't, but it's not actually a problem. You are still able to communicate. TCP uses a window, a sliding window, and it does transmit the available size of that window. So this is what we say when TCP has congestion control. This is what we mean, is that TCP transmits the size of its window. So the sender and the receiver, in most cases, both sender and receiver are, in some cases you're the sender, in some cases you're the receiver. Information is going both ways, right? So both ends of the connection know about the receiving window on the other side. So you're constantly getting updates on the status of the receiving window with TCP. And the available size is the buffer size that that system has, minus the last byte received minus the last byte read. So basically how much room is in the buffer. And this is not necessarily related only to how much is sent. There's other reasons why the buffer might be overfilling besides stuff being sent too quickly. It also might be that the application isn't reading it fast enough. Remember, there might be a lot of applications running on the user's computer. The application might not necessarily read those bytes as fast as they come in. So sometimes bytes just sit in the buffer waiting for an application to read them. So what does the sender do if their partner sends them a receive window of 0, so they have no room left in their buffer? It's empty. In that case, the sender will continue to transmit segments. It will downgrade to the smallest possible transmission unit, which is 1 byte of data. This is a terrible overhead, right? Because you have all those different headers you have to put onto every packet. To send 1 byte of data is really dumb, but that's the way it is. So those segments will be acknowledged as they're finally able to be processed. So some of them will probably be lost if the buffer is actually completely full, but hopefully it can buffer 1 byte. Those segments will get an acknowledgement, and as they get acknowledged, you will get more updates on the window size, because you're constantly getting updates on the window size. That information is in the header, right? So every time you get an acknowledgement, you can update the window size, and then hopefully begin to send more as the window opens up. I think we'll put this off for next time, the estimating of timeout. It's a little bit complicated. It's got math, it's just multiplication and addition, but math is math. There's a Greek symbol in there, so that's pretty tough. So any questions on anything we did today on the retransmission and how that's implemented? We'll probably do the lab and then finish this Or maybe vice versa. I don't know. Maybe we'll finish this and then do the lab. Math, yeah. Oh, math with tears. Especially Greek letter math. That's the hardest kind. I should just replace all the alphas with A's. It immediately becomes easier. That's actually what a lot of textbooks do. Okay. That's going to be it for today. Thanks for tuning in, guys. Like, comment, and subscribe. Pay your taxes, even if you live in Spain. And don't let pedophiles use your homework to transmit their whatever they do. All right, see you guys on Friday.